Hello, everyone, and welcome to today's webinar, Capturing Low-Dose Images, In-Situ Video, and Diffraction Data with the Metro Counting Camera. Now I'd like to introduce today's speaker. Ben Miller has been working on the development of in-situ techniques since 2010, when he began a master's degree project to illuminate TEM samples inside a Techni F20 with broadband light mimicking solar radiation for photocatalysis research. His PhD, working in the group of Dr. Peter Crozier at Arizona State University, focused on the development of operando ETM to simultaneously observe catalyst nanostructure and measure catalytic activity inside the TEM. In 2016, he joined Gatan as an in-situ application specialist. In his role, Ben collects TEM data demonstrating the capabilities of Gatan's in-situ products and presents this around the world. He also provides applications training and support to researchers and helps to specify the capabilities of future in-situ TEM equipment and software. Now, before we get started, I'd like to cover a few housekeeping items. If you have a question, please submit it through the questions pane on your console. Any issues regarding connectivity and webinar viewing will be addressed immediately. We will attempt to answer any questions for the speaker at the end of the presentation. If we do not get to your question, we will follow up later via email after the webinar. Now over to Ben.
Thanks, Jonathan. I'm excited to be presenting today about a camera that I've spent a lot of time testing and capturing great data with recently. I really think that it has the potential to make a lot of experiments possible that were previously impossible, and to really bring counting and the capabilities that enables to a lot more researchers in labs around the world. Today, my presentation is titled Capturing Low-Dose Images, In-Situ Video, and Diffraction Data with the Metro Counting Camera. And that title seems to imply that I'm going to have three sections in my talk, one on imaging, one on in-situ, and one on diffraction. But that's not quite right. I do have three sections, as I'll explain in a moment. But these three types of data acquisition will be interspersed within the three overarching topics that I'll cover today, which briefly are low dose, seeing more, and simplicity. But before I get to that, I wanted to start by talking briefly about the name of the camera, Metro. I was the one who first came up with this name, although many people were involved in the naming process. But it's based not on transit systems or metropolitan cities, but on the Greek word metro, which means to measure or to count. Metro is a counting camera. It counts the electrons one by one, and this is really the fundamental driving force behind a lot of the performance of the camera. So, first question, doesn't Gatan already have counting cameras? How does the Metro fit into Gatan's current portfolio of cameras? We have the OneView and the OneView IS, which many people know well. We also produce a camera called the Rio, which is scintillator-based as well. Metro operates at higher KV, Rio operates at lower KV. More recently, we've developed some direct detection counting cameras, and the first of those was K2IS that was replaced several years ago with K3IS, but both of those operated at higher KV and did not really perform well at 60 or 80 KV. So we had this gap, but now we have the Metro camera that can operate at lower KV between 60 and 200, but it's a direct detection counting camera like the K3. There are three main sections in the presentation that I'll be showing today. The first describes how Metro enables lower dose rates and detection of smaller signals at low kV. I'll also talk about how we can see more in every frame with Metro, and there's several distinct things that I mean by that, and I'll talk about that a bit more. Then finally, I'll talk about why the simplicity of the camera, which is much easier to use than K3IS, for example, does not compromise the power and flexibility that you should expect from every Gatan camera in DigitalMicrograph. I want to start talking about low-dose TEM with a OneView image. This is a OneView image that was acquired at what I would call a moderately low dose rate of 200 electrons per angstrom squared per second for 10 seconds. This is a decent high-resolution TEM image. If I look more closely here, we can see several different lattice spacings. It's not bad. The OneView is, of course, a good camera and probably still the best scintillator-based camera available today. But at this moderately low dose rate, it can produce an okay image. But if we look at the same sample using the Metro with data acquired at the same pixel size, we see that there is much better visibility of these fringes. Now, we're looking at a smaller field of view, and I'll get back to that in the second section of this talk, where I show another comparison. But you can see here that we see lattice fringes out beyond 1 angstrom, where with the OneView, we couldn't. And so I captured these images right after each other on the same microscope from the exact same place. And this is really an effect of the camera, particularly the camera at this moderately low dose rate, where the OneView is starting to struggle a bit to resolve smaller spacings. Here we can see that Metro can capture fine details even at the lowest dose rates. So in the previous slide, we were looking at what I would call a moderately low dose rate of 200 electrons per angstrom squared per second. This was captured at a lower magnification, but this is just 0.74 electrons per angstrom squared per second. So a very low dose rate. Under these conditions, I really wouldn't expect the OneView to give me much of anything. You would just see noise. But with the Metro, we clearly resolve a lot of detail here. And in fact, this is just a small portion of the full image here, which is 2K by 2K. So we can see that by counting the electrons one by one, I captured a high quality image, even at an extremely low dose rate and a low total dose, which is just 25 electrons per angstrom squared. If we look at the FFT, we can also see that there's a lot of information here out to reasonably high resolution. This is not atomic resolution. This is a zeolite sample with large lattice spacings. And the circle you see on the FFT is 0.17 nanometers. So much larger than the 1 angstrom circle that was on the previous slide. But still, this is quite a nice result from the zeolite sample at such a low dose rate. While zeolites, like the one on the last slide, are quite beam sensitive, typically MOFs, like the one seen here, tend to be even more beam sensitive. Of course, there's a lot of variation within both of these classes of material, but here I'm showing that not only can we image this sample, but we can also monitor the damage to the material as a function of time by using the in-situ acquisition of the camera. Counting the electrons one by one means that we can keep the dose rate low enough to observe this material for extended periods of time. But capturing this data with the in situ capability of the camera means that we can quantify the damage as a function of time. You can see that as the video plays back, I'll play this again, the structure is degraded. You see that both in the real space image here on the right and in the FFT here in the center. I should note here that the dose rate was actually changed during the acquisition of this video. So at the beginning, we started out with a very low dose rate on the sample, and there was very little damage over time. And after about a minute at that very low dose rate, we increased the dose rate on the sample and imaged it for several more minutes, all while recording a single in situ video data set. So now if we sum the data from just the first part of the in situ acquisition, when the dose rate was very low, we can get really quite a nice image of the pristine structure. Again, this is the sort of dose rate, less than 1 electron per angstrom squared per second, where a camera like the OneView, a scintillator-based camera, just wouldn't be able to capture much. You would get a lot of background noise from the camera. So the real signal from your sample would be swamped by that background noise. But here with the Metro, we get a really nice result by first, of course, drift correcting, and then summing a lot of frames from this in situ acquisition at a very low dose rate. Here I have another example of imaging a very beam sensitive material. This is probably the most sensitive material that I show in this presentation. It's a 2D polymer material, which I think you could even call a COF, a covalent organic framework. On the left here, you see a rather nice low-dose diffraction pattern, and I'll talk more about capturing diffraction with the Metro in future slides. But capturing a diffraction pattern like this from a very beam-sensitive material is relatively straightforward. So while the Metro produces a very nice diffraction pattern, you probably don't need a counting camera to get a diffraction pattern from most beam sensitive materials, as long as the crystals are large, because you can spread the beam quite far and use a very low beam intensity. And doing this, you can still get a diffraction pattern on a more traditional camera. But high resolution imaging of this sample, as you see here on the right, requires a very low dose rate and a very low total dose, and really pushes the camera. Here, the total dose is just over 30 electrons per angstrom squared, and the spacings that we are trying to resolve are fairly small. So, like the zeolites I just showed, this is not what I would call atomic resolution. These are not individual atoms that we're seeing here. These are molecules in this polymer. But still, capturing data at this high resolution with such a low dose rate is quite challenging. Because the Metro camera is counting each electron one by one, and we have very little background noise, we can still capture some really nice data. And here in the inset, you see just a small portion of this entire 2K by 2K image. And then in the even smaller inset, I'm showing not a simulation. This is actually a real space averaging over portions of this image that results in a really nice high signal to noise picture of what this material structure looks like. If you'd like more information about this data and this material, we have an entire application note on our website that you can find with this QR code. And as I go through my presentation, I'll have several more of these QR codes that can take you to more information on some of this data. One of the most valuable features of the Metro camera, in my opinion, certainly, is how dark the background is. Metro eliminates almost all the background noise, which enables detection of the very smallest signals. Uh, Here I'm showing on the left a video, I'll play this again, of the accumulation of 10 seconds of dark noise from a scintillator camera, again a OneView, with the beam off. So it's not a bad 10-second dark image. It's flat. It's reasonably uniform. The histogram, which I'm showing here on a log scale, has a nice Gaussian distribution. But there's still a large signal intensity in this dark image that shouldn't be there because there's no beam. There's no real signal. So all of this is just noise that would be added to your images. And this is why with a scintillator-based camera like the OneView, you can't image at such low dose rates as you can with a counting camera like the Metro. Here on the right, you see the equivalent 10-second dark image from the Metro being accumulated. And as I play this back, you can see single pixel spots appear periodically. But there are very, very few spots in this 2K by 2K image. And everything that you see that's black is not just a low intensity, it's exactly 0 here. So all that black area would contribute exactly 0 noise to your image. The only dark noise that's being introduced here by the camera are these few spots. Here, there are only 350 false positive counts from about 1.29 billion pixel readouts, which is pretty impressive, I think. And because of this very low background signal, you can capture very faint signals like the high resolution image of the 2D polymer that I showed in the previous slide, or diffraction patterns with very faint spots like I'll show next. In this slide, we see that because the background is so dark, we can get very nice contrast from even faint diffraction spots. Here we counted over 200,000 electrons in the central peak. There are probably electrons that are being missed here due to something called coincidence loss. But regardless, there are at least 200,000 electrons. In this middle red peak, we have about 4,000 electrons. But then in this faint peak out near the edge, we have just 160 electrons. This is still a very clear and distinct peak that's easily distinguished from the noise because there's so little background noise. Most of the background noise that we do see here is not from the camera itself, but from diffuse scatter. So this, and also I would say this peak that's 160 electrons is not even the smallest distinguishable peak in this diffraction pattern. There are even fainter spots here and here, maybe here, here, that we detect, but this one just happened to line up quite nicely with this other spot. But the key point here is that by eliminating almost all the background noise, we're able to detect the very smallest diffraction signals. In this presentation up to this point, I've mostly focused on simple imaging and diffraction with the Metro camera. But there are other things that you can do with a camera like this. We could use this for tomography, for in-situ microscopy, or 4D STEM. I'll talk more about in-situ and 4D STEM later in this presentation. But the point that I want to make here is that counting improves the data across a variety of techniques. We've already talked about how we can get better quality imaging at a very low dose, and I've talked a bit about how we can detect the faintest spots in diffraction. But for tomography, we can reduce the total dose for soft matter or delicate samples. For in situ, we can increase the signal to noise in the individual frames at low dose rates and decrease the effect of the electron beam by operating at the lowest possible dose rate, which you always want to do for in situ. And for 4D STEM, we can get to results, not just data, faster by reducing the analysis time. If we can eliminate pre-processing steps that were previously needed to remove background signals, because there's little background intensity in the counted diffraction patterns. In the section we just finished, I talked about how the excellent low-dose performance of the Metro enables you to capture data at very low dose rates. This fantastic performance is a benefit that counting brings to the Metro camera. But in this next section, I want to talk about how we can see more in every frame with the Metro camera. And there are several different aspects of that that I'll cover here. The first is that we can see more details even with a reduced data size. In one of the previous slides, I showed this same OneView image, and we saw that it's a decent image, but at this moderately low dose rate, the OneView is really struggling to capture all of the high resolution detail that the microscope provides from this area. We can still see some details in this region of the sample if we look at just this small area here. There are several different lattice fringes for sure, but if we look at the Metro with the same field of view this time, previously we had looked at the same pixel size, but now if we go to 6 times lower magnification on the microscope so that we see the same large field of view, we still resolve the high resolution details here. In fact, we can still see lattice fringes out beyond 1 angstrom with the Metro camera, where we could not with the OneView, looking at this same field of view and this moderately low dose rate. This is because the higher DQE of the Metro ensures that there's very little blurring or detector noise. And so all of these very fine details are preserved with the Metro camera. We can see really equivalent or even better detail when comparing the same area, even though Metro is only 2K by 2K pixels, while the OneView is 4K by 4K pixels. The amount of information that you can capture per Metro pixel is significantly better with the OneView, especially at moderately low or even lower dose rates. We can just see more per pixel. The Metro camera also immediately displays more contrast. What do I mean by this? I don't mean more contrast than a scintillator-based camera. I mean that the high internal frame rate of the Metro camera which is 1,477 frames per second, is essential to be able to count every electron individually one by one. The faster that we can capture frames, the more electrons we can detect. But individual frames with sparse counts are not usually valuable. We could give you this huge amount of data. We could give you 492 frames per second. But if we instead sum those frames together, we get a useful image. And so Metro automatically combines individual frames with optional subframe alignment, and I'll show more about that frame alignment in the last section of this presentation. But this summing eliminates the need for post-processing to combine the frames and reduces the file size substantially. And you just immediately get an image with good contrast. Most people just want an image when they press capture, and Metro gives you that. So, and you can see in this small region of interest that the alignment here worked well. The same is true for in-situ videos captured with the Metro. Metro continuously captures the full 2K by 2K resolution at almost 1,500 frames per second, as I just said. But this is just so that we can count the individual electrons. Saving the raw frames in this 105 second long video would generate over 605 gigabytes of low contrast data that might look something like this on the right. And there are very few people in this world who actually want all of that 605 gigabytes of sparse data. Those people are out there, and I am occasionally one of them, but those people should get a K3IS, where we do allow you to save data at higher frame rates. For most people, they just want a data set where each frame is a real image with recognizable contrast. So the Metro automatically sums frames to give you at maximum 41 frames per second at 2K by 2K of much higher contrast video. So for this data set, I actually set the exposure time even longer to 0.1 seconds. So we get 10 frames per second, and each frame in the video has really good contrast. We can see the lattice fringes here in the individual frames. And so we don't have to post-process the data just to see something. We can see useful information right away. We can see images right away. We're not just storing a huge amount of data, we're capturing a useful video. If you do want better temporal resolution, you can bin the data to go faster. And so at 512 by 512 resolution, we could capture up to 492 frames per second. And that sort of speed is also quite useful for 4D STEM, as I'll talk about later. The high DQE at low KV of the Metro means that we can see more of challenging samples like 2D materials. As I said in one of my first slides, Metro is really optimized for between 60 and 200 kV. And so here at 80 kV, it's possible to capture data like this very nice image of molybdenum disulfide. The researcher who captured this, Rachel, she just pressed the capture button with the live drift correction turned on, and the camera automatically aligned and then summed all of the counted frames together to give her this image right away. This is a 2-second exposure, at quite a high magnification, and it wasn't post-processed or filtered in any way. It's just the original drift-corrected image that was produced by the camera with a single click of the capture button. One other thing that I want to point out on this slide is the dose rate used here. So in the whole first section of this presentation, I showed data with moderately low to very low dose rates on the sample. Sometimes just a few electrons per angstrom squared per second, or even less than 1 electron per angstrom squared per second. Here, Rachel used a much higher magnification and pushed the dose rate higher. So you can see that we can capture data with several thousand electrons per angstrom squared per second with the Metro. And this allows this sort of high resolution, high contrast image to be captured easily with the Metro camera in a short amount of time. And while the camera and counting is meant to enable you to push the lower limits of dose rate, as we talked about before, the camera is really also designed to operate at this sort of more traditional high resolution imaging, what I might call a moderate dose rate. The Metro camera can also capture very high quality diffraction. And so we can see more in diffraction as well as imaging. This might be counterintuitive for those of you who have experience with using direct detection cameras, but I expect that Metro will be used as much for diffraction and for 4D STEM as it will be for imaging. This section of a diffraction pattern that we're looking at here is from the OneView, and this is a 5-second exposure. It's a decent diffraction pattern, especially considering the very low dose rate on the sample that was used. This was captured with less than 0.1 electrons per angstrom squared per second. But without changing any TEM settings, I just switched cameras. And when we compare this OneView pattern to the Metro pattern, we see that Metro provides much sharper detail and less background noise than the OneView. And you can see that these brighter spots here are resolved okay with the OneView. The point spread function is certainly worse than on the Metro. These are maybe 3 or 4 pixels full width half max, even though the pixels are physically larger here on the OneView. With the Metro, we have either 1 like here, or at maximum 2 pixels as the full width half max for all of the peaks in this pattern. Finally, for these very small peaks that the OneView does not resolve well because of the underlying background noise, the Metro resolves very clearly, even at this very low dose rate. And again, this is great for beam sensitive samples. Diffraction can typically be captured with a much lower dose rate than you would use for TEM imaging. But with the Metro camera, we can push this even farther and use an extremely small beam dose. Again, in this case, I use less than 0.1 electrons per angstrom squared per second. And I could have pushed that even lower if needed. Here's another example of a diffraction pattern that I captured with the Metro camera. Here, like the previous slide, we're looking at a zeolite sample, but in this case, I was careful to rotate the sample to a zone axis. And so we have a nice symmetrical pattern here. we can see that I can't measure the intensity in quantitatively here in the central peak. The camera can't count that many electrons, and it misses most of them. However, we can very easily and precisely determine the center of the pattern because I didn't have to use a beam stop. We're also not damaging the camera here, as I'll show more clearly in a moment. But since I didn't have to use a beam stop, we can very easily and accurately determine the center of this diffraction pattern. And this also makes it quite easy to focus the diffraction pattern as well, since I could focus it right here on the camera so that the central spot is just 1 or 2 pixels. This pattern also demonstrates the dynamic range of the camera. We can see that in the plot here that there are several orders of magnitude that are well resolved. This plot is shown on a log scale, and we can look at peaks that are several hundred electrons per pixel, like this one just to the side of the central peak. But we can also see peaks that are just 2 electrons per pixel quite clearly. Those are still very distinct above the very low background noise of the camera. And again, most of the background here is real. It's real scatter of the electron beam. It's not the signal we want, perhaps, but it is real signal and not just noise from the camera, as there would be from a scintillator-based camera. Here I'm showing that Metro can capture in-situ diffraction as well. I'm melting and recrystallizing some tin nanoparticles, and we can see that as the sample melts, all the lattice spacings disappear, and as it recrystallizes, they reappear. And in fact, it turns out they reappear in different locations each time because the sample doesn't interact strongly with its support. And so each time the particles crystallize, they do so in different orientations. The central beam, the direct beam, is too intense here to count every electron. And you can see that it has this sort of strange black and white contrast, like I showed on the last slide. But the sensor is not damaged. And this is one of the things I like about this video, because if I play this again, during this single in-situ video acquisition, I switched the microscope from diffraction to imaging, and then back to diffraction again. And because I switched directly from diffraction to imaging, let me see if I can find that spot here. There we go. We can see whether the direct beam was damaging the camera at all. If the central beam had damaged the camera even slightly, you would start to see a little burn spot in subsequent TM images, but we don't see that here. And that's because even though this central beam is too intense to actually count every single electron, it's not too intense for the camera. It's not even close to doing any permanent damage here. And so we can look at diffraction patterns like this without a beam stop, which allows me to, again, very easily find the center of the pattern and focus the pattern. And if you want to learn more about capturing diffraction with the Metro or the K3, we have a detailed application note that you can find on the Metro page of Gatan's website or directly access with this QR code here. In this final section of my talk, I want to talk about the simplicity and ease of use of the Metro camera, but also how the simplicity doesn't compromise the power and flexibility that you get with all modern cameras in DigitalMicrograph. Ironically, it's actually rather difficult to demonstrate the ease of use of our cameras in a PowerPoint. It's really more compelling to see the ease of use through a live demo, but I'll give this a shot anyway. So you see here the user interface of the Metro camera for capturing images. This is very similar to the OneView camera interface. We first set the mode, either imaging or diffraction and the binning. We then set the view exposure time and start the live view, and then set the capture exposure time and press capture. And that's really all there is to it, to capture a single image. If you want, you can check this correct drift checkbox, and I'll show more about that on the next slide. But this interface is really designed to be simple and also to be very similar to the OneView camera, which many people are familiar with. If your sample is moving, and during in-situ experiments, it often is, drift from the sample can blur your images. Also, if you just move to a new location, often there can be residual motion. With the Metro camera, like our OneView and Rio cameras, we have this drift correction checkbox. So that with one click, you can immediately capture data with correct subframe alignment to give you a much better result. This eliminates the need to take shorter exposure times or to wait for the drift to settle before you capture an image. You can just immediately capture an image and get a nice drift corrected high resolution result and just work faster and more easily. In-situ acquisition is actually standard with every Metro camera. For other Gatan in-situ cameras like the OneView or the Rio or the K3, which we also produce, there's an in-situ option. So you have to purchase the optional IS upgrade. With Metro, we don't have an upgrade. Every Metro is always in-situ capable. And what we mean by an in-situ or IS camera at Gatan is that we can capture video data sets with full resolution, full frame rate, and full bit depth in DigitalMicrograph format. So you get all of the information that you'd get with a single image in your video. We also have the look back buffer, and this allows you to watch the live view. And when something interesting happens, then you can press record, and it automatically appends that buffer of data. So you still capture the initial onset of those dynamics that you saw. And this means that you're less likely to miss unanticipated events, but it also means that you can capture just the most important data rather than trying to capture the entire experiment from start to finish, which might result in a massive amount of data. Though, of course, you could do that if you wanted to, since the PC comes with several terabytes of storage space. We also now have time lapse. This is a new feature in the latest version of our software that works with all of our in-situ cameras, where we can capture just one image every n seconds or every n frames to store less data during long or slow experiments. And here is a screenshot, a screen capture showing an in-situ acquisition. I started the recording, and then I'm using the built-in temperature control for the Den Solutions wildfire holder that we have here in our software. That's a free feature of recent versions of DigitalMicrograph, the holder control. Here, the sample is an iron oxide hydroxide sample, and I'm heating it up to 900 degrees C. And I'm recording this data set, and it just records for as long as I want. And then when I'm ready to stop the recording, I just press the stop button, and it will finish saving the data. So maybe I'll move ahead here to where I do that. So I press stop, uh, and it always keeps up with saving the data in real time. I don't have to wait for a while before I continue. So now the live view can just restart immediately in case I want to see what's happening or capture another acquisition. We don't have to wait a while for the data to process or be stored. It's all keeping up in real time. On this next slide, I want to show how we can then visualize and process the data. Capturing the data is essential. Obviously, we need to have a camera that can acquire data at the frame rate and the resolution and the quality that we need to get good results. But capturing data is not enough. You always have to visualize, process, and or analyze the data for that data to be useful. I often say that data on a hard drive is no more useful than the atoms in your sample. You can't see the data on your hard drive. You can't come to scientific conclusions about data sitting in a hard drive. You have to visualize it, process it, analyze it. In situ processing and visualization are standard with every in situ camera at Gatan, including the Metro camera, using the free in situ player and editor. Here I'm showing an example where I'm playing back the data with this in situ player, and all of the data that's displayed on this workspace is automatically synchronized. So I can see the original data, but I've also used the free tools in DigitalMicrograph to drift correct and to sum frames together to give me a better signal to noise view of the data here in the center. And then the live FFT is, of course, by definition, always live in DigitalMicrograph. Also, here at the bottom, we have the in situ holder data from our Den Solutions wildfire holder that was also automatically captured with the image data. And now it's automatically synchronized as I play back the data. And this automatic synchronization and visualization is all free. So if you go to a national laboratory or some other institution's TEM facility and you've captured some data with one of our in situ cameras, you can take it home and use the free version of our software with this free in situ player and editor to do all of this visualization and processing of the data. There's a lot that I could explain here about the in situ player, but I don't want to spend a lot of time talking about all of this in detail today because there's a whole series of tutorial videos on our YouTube channel, as well as an entire webinar like this one focused on just the in situ player and editor. So I encourage you to find those and watch them if you're interested in more detail. I do want to emphasize here that this is the same in situ player and editor that we use for the OneView IS, Rio IS, and K3 IS. In fact, the in situ player and editor can even be used with the new in situ eels features of our Continuum IS as well. The Metro camera also always reports the dose rate. You can see that here at the bottom of the screen in what we call the dose rate monitor. This gives you the average dose rate over the entire image. But if you put a region of interest on the image, then these numbers will be from just that region of interest, as we see here. This is especially valuable in cases like this image, where you have some area in the field of view that's just the vacuum with no sample, because measuring here will give you not the dose rate that made it through your sample, but the incident dose rate that hit your sample. There are 3 different numbers in the most recent version of this dose rate monitor. The first is the camera dose rate in electrons per pixel per second, which allows you to achieve the optimal DQE with the camera, to operate the camera in the best range. The second number is the sample dose rate in electrons per angstrom squared per second. And this is important for quantifying beam effects, especially during in-situ experiments, where the total dose is always increasing. And the third number is the total dose per frame. So for single images, this is based on the total exposure time for that image. And for the live view, this is based on the live view exposure time. And always knowing the dose can really help you to quantify the beam effects on your sample. There are several more ways that I want to talk about briefly in which the simplicity of the Metro camera doesn't compromise the power and flexibility of DigitalMicrograph. The camera, like all modern Gatan cameras, instantly corrects all live view and captured data with dark references and gain normalization. In the case of Metro, it's also always counting the electrons one by one in real time. It also stores metadata automatically as well, as I showed earlier in the webinar. And so a temperature plot was stored automatically when we captured this data, and then displayed and synchronized when I opened the video dataset. Of course, you also have the option to automatically save and name files with a variety of naming conventions and file types, just like with any Gatan camera. We also have options for scripting, either with DM script, as we've had for decades, or Python scripts that we've added just a few years ago, so that you can do advanced acquisition and or processing of data. I'm one of those people who loves to write scripts to do customized data processing. So I'll talk a bit more about scripting in DigitalMicrograph on the next few slides. But the point here is that all of these things that come standard with all of our modern cameras in DigitalMicrograph are, of course, included with the Metro camera, even though the camera itself is meant to be very simple and easy to use. These features really complement that ease of use. It's easier than ever today to do custom processing of your data. Now that we have Python directly embedded in DigitalMicrograph, you can write a Python script, open this in DigitalMicrograph, and run your .py file directly within DigitalMicrograph. The particular script that produced this color image on the right here is one that I wrote, and it's available from the Python script collection on the Gatan website, which you can reach directly with this QR code, and you can get a lot more information about how to use Python in DigitalMicrograph on our website, including, again, an entire webinar that I presented on this topic. I'd love to show more about processing the live view in real time with Python, but I'm running out of time here, so I'm just going to skip over this slide. But the last thing that I want to cover in this Metro webinar is some optional features to extend the camera functionality. The first one is holder integration, to integrate data and even control selected holders. Then StemX, which is our product to capture 4D STEM data with an in-situ capable camera. There's TrueAlign that allows us to align features with digital rotation. And finally, digital montage to capture large fields of view with exquisite detail. And I'll talk a bit more about each one of these in the coming slides, but we're almost out of time, so I'll move quickly here. Holder control and integration are enabled by a free software license. This is applicable to all in-situ capable Gatan cameras, and even our newer in-situ continuum EEL spectrometers. The available features vary for different holders, but briefly, control is available for heating of all dense solutions holders and for Gatan holders that are controlled with the 1905 controller. So if you purchased a Gatan holder in the past few years, you likely have this controller. If you purchased your holder a long time ago, maybe you have this or maybe not. Data integration is possible with Den Solutions Impulse, with Protochips Axon, or with, again, with Gatan holders controlled with the 1905. The next option that we have to extend Metro, and I think by far the most powerful one, is what we call StemX, which is our product for collecting 4D STEM data. This is a map from a data set where I captured 128 by 128 scan pixels with 512 by 512 diffraction patterns, like the one you see here, at each scan position. This data was collected in about half a minute and then processed by a Python script in DigitalMicrograph in about 1 minute. Again, the Metro's capabilities for diffraction with sharper detail and less background noise can be utilized here to collect 4D STEM data as well. Here's another example of a data set I collected with Metro and StemX. Here, 512 by 512 scan positions. Over 262,000 total were captured, and this took about 9 minutes to collect. Then the data was again processed with the same Python script in DigitalMicrograph, and that took about 5 minutes. Another option to extend Metro is TrueAlign. This allows us to precisely align certain sample features with digital rotation. And in the video here, you see how that works. I can just draw a line on the image, select to align it vertically, and now this image is aligned, both during the live view and for single image capture. This does crop the data because it's a digital rotation, but especially for semiconductor samples or any application where you want every single image to be captured with a very specific sample orientation, this can be quite useful. Digital montage is another optional feature that you can purchase to extend the Metro camera. Here we can capture a much larger field of view by capturing a whole series of images. This example shows 4x4 individual image captures. Digital montage automatically captures those and stitches them together in one click in DigitalMicrograph. So if I look at this demo video here, we can see this running. I just click the capture button here in the montage palette, and now the software automatically captures the images. Some calibrations are required to make this work, but the software walks you through exactly how to capture those calibrations as well. And then after the images are captured, the software automatically determines the exact offsets of the images and stitches them together, and you get this impressively seamless large image that can be viewed and processed like any other image in DigitalMicrograph. So in summary, the Metro is a cutting-edge counting camera that I think will really enable groundbreaking imaging, diffraction, and in situ studies. Metro enables lower dose rates. It allows you to detect the smallest signals, even at low kV. You can see more in every frame with Metro, whether that's nice contrast in every in situ frame, high quality diffraction, or just the amount of information that you can see with 2K by 2K pixels in imaging mode. And finally, the simplicity of the camera and its user interface for taking images doesn't compromise the full power and flexibility that you get by working in Gatan's digital micrograph software. So with that, I'll take any questions that you have. Again, you can submit those using the questions pane. I'll try to answer as many questions as I can now live, but I know we are at the hour right now, so probably won't have time to answer too many. If I run out of time, then I'll send you an answer by email. Let's see. One question has come in. Is Metro better than K3 in terms of DQE, or are there any improvements in performance in Metro compared to K3? So the I guess the simplest answer to that question is going back to one of my very first slides about the KV range of the camera. So K3 is really designed for operating at high KV, 300 kV, 200 kV. The Metro is optimized for 60 to 200 kV. So at 60 and 80 kV, it's certainly better than K3. The DQE would be better at those low voltages. At 200 kV, likely not. I expect K3 would be better at the highest voltage. But they're fairly comparable, I would say. But yeah, the main, if I could come up with a benefit of the Metro versus K3, it really would be simplicity. So yeah, let me see. Are there other questions here? Let's see, how can you automatically align individual counted frames if there is very little signal in each one? So we don't align frames at 1477 frames per second. That's the full sensor frame rate of the camera. We're not trying to align those frames. We do align frames at 41 frames per second at the full resolution. And I can't describe all the details of the algorithm, but the algorithm is adaptive, I would say, and surprisingly robust. So while like all drift correction, it can sometimes fail. The drift correction works, as I would say, surprisingly well at very low dose rates, where you, as the user, see very little. But there's still enough information in the image for the algorithm to align the frames at 40 frames per second. Let's see, another question. You mentioned that the background in the diffraction patterns is real scatter. What could you do if that scatter is making it difficult to see the faint signals you want to observe? So let me go back to one of these slides, maybe this one. And so I mentioned that this background signal is real scatter. Um, and I say that because if this was noise from the camera, the noise would be flat. It would be much more uniform across the camera if this was just dark noise. Um, but this background that we're seeing is decreasing rapidly over time. This is actually scatter from the electron beam. And so the best thing to do is to capture filtered diffraction. And Metro can't be placed at the end of one of our GIFs, our EEL spectrometers. But the K3 and the Stella cameras can go at the end of one of our GIFs, our continuums. And so you can capture counted diffraction with a K3 or with a Stella that would also be filtered, and that would really eliminate a lot of this background diffuse scatter. Let's see, is the Metro better than the K2 at 200 kV? So I don't have the curves or even the spec numbers all in my head. So I might have to look that up to see, numerically, is it better? The Metro is a much better experience to use at any voltage than the K2, particularly for in situ experiments. So if you have a K2 IS that can capture in situ data, in situ could not be counted with the K2. And so all in situ data with K2IS, while it could be very high frame rate and decent quality, it is a direct detection camera, but the K2 wasn't doing counting during when you're capturing in situ data. And so the quality was much worse in the IS version of the K2 for in situ experiments than on the Metro, where we're doing counting always in real time, even during in situ experiments. It's also just, overall easier to use the Metro. There are some pitfalls that you can run into with the K2 that we've just taken care of all of that with the Metro. It's very easy to get great data with the Metro camera, where with K2 it could be you need more skill, I would say. Even a novice user can use the Metro to capture great data. Okay, maybe I'll do one more question, and then we're almost at 10 minutes past the hour, so I should really stop here. So let's see, which question do I want? So the last question, what is the dark image or the dark spot in the center of the selected area diffraction patterns that you showed? So let me go back maybe to this slide. So this dark spot that we see in the center of the diffraction patterns is a result of the counting algorithm. First of all, it indicates that the intensity is orders of magnitude too high to count every electron. So not just 2 times too high, but maybe 100 times too high to count every single electron. This spot is not an indication of damage. We're not damaging the camera here. And actually, I find this spot quite convenient, to be honest, in practice, both for focusing the pattern and for finding the pattern center. It just makes those very easy to do because you can very easily see the focused central spot in the middle there. And if I go to the next slide here, if you want more information about this, you can check out this app note that's on our website. So anyway, thank you all again for joining this webinar. I'm excited to be presenting a lot of this data, and I hope you're excited by the potential that this has for your experiments. And I can collect some nice data myself, but I'm not doing a whole lot of science. I don't have time for that. But I'm excited to see some of the science that's going to come out of this. So thank you all again.